Welcome everyone. My name is Lasse, and in today's lecture I'm going to give a brief introduction to model predictive control. Now, before we get started, I want to motivate this problem with this autonomous driving scenario. So imagine that we're controlling a car here at an intersection in Bonn, and we are tasked to sort of safely navigate this car over this intersection. Now, if we were to solve this task, there are several steps involved. So typically, we would first run some kind of perception pipeline that will detect, that we will use to detect other cars, and then also detect the drivable area of the road here marked in green. And then in the pre-processing step, we would have some high-level planner that gives us a rough plan. So imagine that here we want to take a right turn at this intersection. And in today's lecture, we are looking at this scene in an abstract perspective. So we are assuming that we are given a reference plan that we want to follow, and we are given a state estimate, which includes the position and velocity of our own car, and then also of other cars that we may treat as obstacles. And we are asking the question, how can we find control inputs? So in this example, the steering commands and the acceleration and brake pedal commands in order to achieve this plan. Now, in previous lectures on this channel, we've already discussed ideas for control, in particular reactive control. And so here's just a quick reminder of how that worked. And so in that setting, we would typically decompose the problem into along different dimensions. So for example, for this bicycle model of the vehicle, we would decompose it into a longitudinal problem where we propose a controller to control the velocity of that vehicle. And one choice that we may take is a PID controller. And then on the lateral dimension, so for the steering commands, we would use, for example, a Stanley controller. And for example, the Stanley controller is just this law where we plug in the cross-track error, so the lateral deviation from the reference trajectory. And then using this law and multiplying this error with the gain, we can map that to the steering command delta. Now, while these kinds of controllers are very appealing due to their simplicity, there are several limitations which motivate the use of the control techniques that we discussed today. So here's the list of the limitations, or at least an abstract view of that. And so the first kind of limitation that is very important is that it's not trivial to extend these controllers or these ideas that, for example, we have from Stanley to more complex systems. So these kinds of controllers are kind of rules that we can write down for a very specific system. But if, for example, we were to control a legged robot, then we obviously can't use the Stanley controller, and we have to sort of rederive the whole controller from scratch. And it's not immediately clear how to come up with such a rule for an arbitrary system. Then furthermore, there are these control gains, for example, in Stanley, that we have to tune, and we kind of have to make a choice. And this tuning can be a very tedious heuristic and manual process. Then furthermore, we had to decompose the problem into sort of smaller problems for which we can write down these rule-based controllers. And so here we decompose it into a longitudinal and a lateral controller. And this kind of decoupling ignores the coupling between the two dimensions. So imagine that you're controlling a car and you want to safely steer around a corner. In that setting, you would want to reduce the velocity in order to make steering around the corner simpler. But here, when you decouple this, the PID controller doesn't know about the fact that the Stanley controller has a hard time making its turn around the corner. Then another important limitation is that, for example, the Stanley controller is a rule that we can only use to track a given reference. But if there's a more complicated task, or we may want to avoid something like constraints or maybe other obstacles, then this is not immediately captured by this kind of controller. And finally, these controllers always only take in a snapshot of the current time, so they evaluate the current cross-track error, or maybe a filtered version of that, but they don't look how their decisions affect future decisions. And so they always sort of reactively mapping the current state or the current setting to a control command. And yeah, so these kind of limitations bring us to the topic that we're discussing today. And so model predictive control makes use of optimal control technique, and optimal control is asking the question, how can we best control the system? Now, in order to formulate a given problem as an optimal control problem, there are several ingredients involved. And this first ingredient that we need in order to model a given problem as optimal control is a model of the system dynamics. And this model we will use to predict the evolution of the state for the given inputs. So the dynamics model F maps the state, which may be, for example, the position and velocity of our vehicle, and the input, which will be the steering and brake pedal commands, to the next state, so to the state at the next time step. Right, and so given the sequence of inputs, if we have a model, we can predict the evolution of the trajectory, so the evolution of the state into the future. Now, for our example of a bicycle, or for our self-driving car, we could use the model of a 2D kinematic bicycle that you can see here. So there the state would be given by the position in x and y, then the heading psi, so the heading of the vehicle, then the velocity of the vehicle in the longitudinal direction, and the steering angle delta. And we can write down, for this sort of kinematic abstraction of the car, we can write down the state evolution using this equation, where our inputs are the acceleration and the steering rate. And so in any case, this model, or the model that we will use, will always be an abstraction of the real dynamics. So of course, this neglects many details, maybe drag or other effects. But yeah, we just need a model with which we can sufficiently well predict the state trajectory of the system. Yeah, and we will go into some of the details of the trade-offs involved later. Now, once we have dynamics, we also need an objective, and this objective is used to assign a cost to a given trajectory. So it's rating how good is a given trajectory for the task that we try to accomplish. And so this objective is written down as a cost function, which depends upon the sequence of states x and inputs u, and maps it to a scalar. And so here we would typically write it down as a time separable cost, where g only takes the current state and input at time t. And then the total cost j, is the sum of these individual time costs or stage costs. And so, for example, for the problem of reference tracking that you can see below, we can write down this cost as this squared sum of terms, where for the state, if this dashed line is the reference that we may wish to track, and this red line is the prediction that we would get for a given sequence of inputs, then we can compute this tracking cost as the sum of weighted sum of these errors, E, where the errors are the difference between the trajectory in red and the reference trajectory. So the state where we are at according to our prediction, and the state that we would want to be at that time step. And then we weigh these errors with this weighting matrix Q to sort of say which part of this error, which is a vector, is more important than others. And then also we will have some cost for applying steering commands. So in order to encourage or to prefer trajectories that have a low, for example, low acceleration or low steering input. So we sort of prefer smooth trajectories that are not very jerky. And so the task, or the task of the objective, is to encode which trajectories are preferred over others. So the objective encodes the task that we try to accomplish, in this case, tracking the reference. And then the third and final ingredient of this kind of formulation of an optimal control problem are constraints. And constraints encode domains of allowed states and inputs. And so we would write these constraints with these calligraphic X for the state constraints and calligraphic U for the input constraints. And to make this a bit more concrete, here's an example of a state constraint. So we can use this constraint, for example, to encode areas that we don't want to enter with our system. For example, if there was an obstacle here centered at the origin, marked in red, then we could express this as the following constraint. We want that, if you use this bicycle model that we've seen earlier, we want that the squared position px plus py, so the squared x coordinate plus y coordinate, must be greater or equal to r, which is the radius of this obstacle. And that essentially just encodes that our trajectory must lie outside of this circle, if the circle is centered at the origin. And so, these are the state constraints, so they will only depend on the state variables. And then we can also have input constraints that you can see on the right. So for example, we may wish to never exceed a certain acceleration due to some friction limits of our tires. And then we could sort of have a box constraint, so an upper and a lower threshold that our acceleration cannot exceed or must not exceed. And so here this profile is sort of bounded below by a min and above by a max. And we would write that as the following inequality. So a must be greater than a min and smaller than a max. And using these kind of inequalities or description of sets where our states can be in, we can sort of encode these state and input constraints. Now, to summarize, using all of these three ingredients, we can write a given problem as an optimal control problem by using this mathematical formulation. So we can write it down as a constraint optimization problem in which we attempt to minimize the objective J by choosing the states X and inputs U, so a sequence of states X and inputs U into the future. But we are not allowed to choose arbitrary states and inputs, but rather they must be consistent with the dynamics that we've chosen. That is, we have constraints that each of the next states must correspond to our dynamics model. So the trajectory must be dynamically feasible. It must be achievable by the system model that we took. And then also we have these state and input constraints that I've just talked about. So we can't arbitrarily choose X and U because X must always be in the set of feasible states, so calligraphic X, and U must be in the set of feasible inputs, calligraphic U. And then the final constraint that we also add is that at the first time step, our trajectory must agree with the initial condition that we have from our state estimation pipeline. So all our plans that we make from here into the future, they must start at our current position. Okay, and so when we have this sort of mathematical description of the control problem, then we can attempt to solve it. Now, the bad news is that in general, there is no closed form solution to these problems, and instead we have to use numerical methods in order to do that. The details of how that is done are beyond the scope of this lecture, but in practice you can often get away with encoding your problem in one of the existing modeling languages for constraint optimization. And so there are tools with very high-level interfaces such as Casadi, which has an interface in C++, Python, and MATLAB, or JUMP, which is a constraint optimization library in Julia. And the beauty of these libraries is that you can take this mathematical description of the problem. So here, a very simple problem over two decision variables, X and Y, with this very simple objective and only two constraints. And if we were to encode this problem, for example, in Casadi and Python, we can just declare what are the variables so the decision variables that we can use to minimize the cost. Then we symbolically describe the objective and the constraints, and then we can just call a low-level solver. And so if you know how to write a given problem or how to encode a given control problem as this in this constraint optimization form, you can already use these libraries to accomplish the task. Now, are we done? Unfortunately, we're not. So just using this optimal control technique that I've just mentioned will not be immediately successful. And there are several reasons for this. So if you imagine that we just sort of solve this optimal control problem and then we take the sequence of controls that we had and play them out to achieve our task, we would get to the problem that we use the prediction model that will always be wrong to some extent. So the prediction model was an abstraction of the real system, and so it will have errors. And because we would take sort of multiple steps after another, often these errors will accumulate over time and they will result in a diverging trajectory of the system. So if you imagine for the same set of inputs, so the same set of or sequence of inputs, so the same sequence of steering commands and acceleration and brake pedal commands, if we apply them to the real system, we may follow this blue trajectory. But then if we apply this sequence of states and this sequence of controls to our prediction model, then we would follow this other trajectory. And therefore, if we just sort of play out our sequence of controls and inputs in open loop, we will not accomplish our task very accurately. And the second reason why just applying this technique is intractable or is not a good idea is that even if we had the perfect model, so maybe we perfectly knew how our system behaves to the inputs that we apply, then we may have a very long task horizon. So imagine that we have this car that is tasked to drive around this loop. So it's tasked to follow this dashed reference line. And if we were to write this down as an optimal control problem for this entire sequence on this entire lap, then we have the problem that we have a lot of time steps that we have to consider in our optimization, and this is typically intractable. So we get a very large problem that is hard to solve in a limited amount of time. And therefore, model predictive control adds one further idea to this framework of optimization, which is the idea of receding horizon control. And so the idea that is added there is that rather than optimizing for the full trajectory into the future, we start at the current time step and we consider only the current state. And then from there we only we take a look ahead. So we only consider a limited preview into the future, maybe the next 50 steps. And so we measure the state and then we task our optimizer to optimize the next 50 time steps into the future. And from these 50 time steps, so we have the optimal solution for the next 50 time steps from our optimizer. We'll then only take the very first input. So we'll only apply the first input to the system and then measure again the new state. So we would then replan from there. And so the idea is rather than playing out these inputs in open loop, we always only apply the first one and then measure again where that brought us. Now schematically that would look as follows. So for this example of driving in a lab with an autonomous vehicle, imagine that we are here at t0 and then rather than planning for the full lap, we only plan for the next, say, 50 time steps. Then this may be the optimal trajectory that we get from our optimizer at this current time step. Then we apply only the first bit of that input sequence, so maybe just the first input. And then we'll end up somewhere here. And the point is that we may not exactly end up where we plan to be, but we will hopefully be close if we have a reasonable model. But because we measure again and we now replan from here again for the next 50 time steps, we are able to sort of capture these errors because we always query the system for the true state. And so we replan from here and then we get the next trajectory. So the advantages are that we are able to account for errors because by replanning we introduce feedback and then also reduce the problem size. We reduce the problem size because we only need to ever plan for the next, say, 50 time steps here, rather than for this whole loop. Now, from an algorithmic perspective, this is sort of the summary, and it's really just what I said. So as an input, we take the objective, the dynamics model, a planning horizon, and for a local solver, we typically also need an initial guess to speed up the solve. And and so we will initialize our controls with this initial guess, and then we loop over this following sequence. We measure the state, so we get the sort of the current state from the state estimation pipeline, and then we plug in our current initial guess into the solver together with the objectives and the dynamics. Then we get the sequence of controls. We get only the first control input and apply that to the system, and then we start again. And one important point here is that because the controls between different time steps typically only vary by a small margin, it is a good idea to reuse the controls from the previous time step and use them to warm start the next solution to make this solution process faster, because we have to do it online. So we have to be able to do it at a high rate. Okay, and if you do all of this, then here's a small toy example of this small blue car steering around this track, which is given by this blue, rather jerky reference. But because we run a model predictive control and we only allow for dynamically feasible trajectories, the closed loop trajectory that we get is this very smooth orange line, which we get from these green predictions at every time step. Now that we've discussed the high-level idea of model predictive control, I want to briefly discuss the different design parameters that are involved in order to successfully design an MPC controller for a given system. And so these design parameters range from the prediction model that we use in our optimization, over the cost function that we use to encode the task, to the prediction horizon, which is the number of time steps that we include in our optimization at every time step. So at every optimization step. And then finally, I will also discuss terminal constraints, which are additional constraints that we can add in order to improve the safety of our system. Okay, so let's start with the prediction model. And so the general trade-off that we have to solve when choosing a prediction model is between accuracy, that is, we want to be able to very accurately predict how our inputs affect the future states of the system, and complexity, that is, we want to have a very simple model that allows us to solve this optimization problem quickly. So we want to have a very small model with only a few number of states. And so these two things are typically competing. So often a very accurate model has a lot of states in order to capture the high fidelity details. And finding a good trade-off here is the main task when choosing for a model family. For example, for this car, a bicycle model, a kinematic bicycle model may be good if we're at low velocities, but then if we're at higher velocities, we will also have to include dynamic effects such as friction and aerodynamic drag. But once we've committed to a model family, so we kind of know the model class that we are in, then if we only have some parameters that we want to estimate, so for example, we want to estimate the drag coefficient or some friction parameters, then we can get these in a very principled way through a data-driven approach. And the way that we would do that is that we can collect a data set of the real system behavior, here denoted with calligraphic D. And each of the data points in that data set is comprised of these tuples of x prime d, which is the next time step that is obtained when you apply ud, so the input ud at the state xd. And the way that you would typically get this data set is, for example, if you imagine for your car, you can just drive that car on the loop that we've just shown earlier. So you can just drive the car and record the sequence of inputs and the resulting states, and then you can chop up, so you record that from your true system, and then you can chop up this trajectory into these tuples to compose this data set. And our task will then be to, if we have this data set, we can optimize the unknown parameters, such as drag and friction. We can collect them into this parameter vector theta, and then we can again cast this as an optimization problem. So we can say that we want to minimize a loss function over this data set by choosing a good candidate, or making a good choice of these parameters. And this loss function is the squared sum of prediction errors between, or the squared sum of errors between the predictions that we would make from XD in our data set when applying input UD and the true next state. So this is what our model would give us for a given parameter theta. This is the state transition that the model would give us, and this is the true next state. And we want to minimize the squared sum of these errors. Right, so the second kind of parameter that I just want to touch on very briefly is the cost function. So the cost function is used to encode the task. And when you design a cost function, you have to be careful, or you have to make sure, you have to understand that you induce a certain optimal behavior. So for example, if you look at this task of following this road, one way in which you can design a cost for this problem is by placing a reference at the center of this road, and then you can just use a squared penalty, such as the squared cost function that I showed earlier, where we penalize the cross-check error. But the behavior that we get from that is this very sort of conservative line that is trying to stay near the center line, because that's exactly the objective that we encoded. For an autonomous driving scenario, so a non-competitive setting, this may be the right way of encoding this task. But if we want to have more competitive behavior, so for example, we may wish to drive along this track as fast as possible, then this is not a very suitable formulation, because driving fast along this lane, along this road, is not easily achieved if we are constrained, or if we sort of encouraged to stay along the center. In that case, if we want to drive fast, a better formulation of the task is that we just include the track bounds as constraints. So we say that all these positions, so all the states that we consider must be within the track bounds, and then we only use the cost function to encourage progress along the track. So, for example, we have a penalty for low velocities. And then the third kind of parameter is the prediction horizon, so the number of time steps that we consider in our optimization at every round. And so there again we have a trade-off. So we ideally want to have a short prediction horizon, so that we have a very simple optimization problem with only a few number of time steps that we have to consider. But if we only consider a few time steps into the future, then we get very myopic, so very short-sighted behavior. And this kind of myopic behavior can either be inefficient. So imagine in this scenario where this car is placed down here on the left and we only consider the next 5 time steps, and maybe inefficient because here we decide to accelerate and then we have to brake a lot in order to make the turn, and so we're sort of wasting our control authority to correct the mistakes that we made earlier due to this short-sightedness. But it may even be unsafe. So imagine that here we decided, because here we only see the straight segment, we decided to accelerate so much that we're not even able to keep the car within the track bounds once we see that this road is making this turn here. And so one way in order to avoid this sort of unsafe and inefficient behavior is by making this trajectory longer, so taking more time steps into account, so using a longer prediction horizon. But another way that you can achieve that is by including terminal constraints. And these constraints are additional constraints that ensure recursive feasibility. So with feasibility, I mean that at this previous setting here, where we are not able to make the turn, the problem became infeasible in that there's no states, there's no control inputs that we could apply here that are in the allowed set of controls, so in calligraphic view, that would keep our car within the track bounds because we were already so fast. So this problem became infeasible. And recursive feasibility means that if we have the correct, if the true model of the system agrees with the prediction model that we have, then this problem will always be solvable, even if we only consider a limited number of time steps. So even though we don't see this corner coming. And one way that we can achieve it in this very problem where we have a static environment is that we can constrain the velocity at the end here to be 0. And that means that we are only considering plans for which at the end we can bring the system to a stop. So we can bring the system to a stop over our prediction horizon. And that will implicitly prevent us from ever going so fast that we could not bring the car to a safe halt when maybe here comes a very short or a very sharp corner, or maybe even a wall or something appearing. Okay, so now to summarize the pros and cons of a model predictive control, in particular in contrast to reactive control, we have seen that we can explicitly handle constraints that we can use to encode obstacles, so positions of obstacles, or the track bounds, as in the previous example. Due to this receding horizon control scheme, we explicitly also account for future decisions. So our optimization procedure explicitly accounts for how does the controls at this current time step affect the controls at a later time step, and we're also doing that coupled, so we're controlling steering and acceleration simultaneously, for example, for this car. And finally, we got a very systematic procedure in order to construct a controller. So all we need to do is write down the dynamics for the system and the costs, and then potentially additional constraints. And once we have that, we can hand this description of the problem over to an optimizer to get the control law, and we don't have to derive this sort of rule-based controller by hand for the given system. A downside of that is that we have to solve this optimization problem online, and so these kinds of methods, they will have higher computational and complexity and more memory requirements than a simple rule-based controller where all you need to do is quickly evaluate, for example, the cross-check error and plug it into the simple rule. To finish this section on model predictive control, I want to highlight a few applications of these techniques in the wild. And the first kind of example I want to show you is a learning-based model predictive controller from Ugo Rosilio from UC Berkeley. And in this work, they have extended the idea of vanilla model predictive control with learning of a cost term at the end of the horizon, which is used to account for decisions beyond the prediction horizon. And you can see that when they apply this idea to a full-size car here on a racetrack, in the beginning this car is driving very slowly and conservatively because it doesn't have a good idea of the cost to go, so the cost beyond the cost beyond the prediction horizon. But after driving a couple of laps on this track, it has sort of gathered experience and is able to compress that into this cost to go term, and they are able to even reach the friction limits of the tires here in this example. And the second example I want to show you is a whole body model predictive controller from Marco Hutter's lab at ETH Zurich, or the Robotics Systems Lab. And this is a great example that model predictive control is applicable beyond these car-like models like that we can typically capture well with bicycle models. So here they're controlling this wheeled legged robot to perform all sorts of tasks, different gates, moving over obstacles. And so you can see that model predictive control is a very expressive technique that can be applied to a wide variety of different systems. Now that you've seen the sort of expressiveness of MPC, I also want to briefly highlight one of the main limitations of model predictive control, which arises when interacting with other agents. So if there are thus far we've always considered scenes where there's only a single agent. So there was only this autonomous car that we maybe want to control over the track. But if there are other agents in the scene, then we kind of have to account for them. And one very traditional way that we could do, could use to do this is that we can treat other players as dynamic obstacles. So we can predict where they will be in the future with some motion model, for example, a constant velocity model, or with some more elaborate model that we're getting from some prediction pipeline externally. However, the problem is that we typically can't statically predict where other players will be in the future, because these players plan as well, and thus their position in the future will depend on our own actions. Because if I sort of drive close to this car, for example, it may sweep to the side. And so this decision-making process of multiple players is highly coupled, and that is something that is not captured by model predictive control, at least not by the vanilla formulation. And so one extension that I just want to briefly provide is an extension to dynamic games. And so here I just want to highlight the main difference to an optimal control problem. You will see that on the high level, this problem looks very similar. So in order to cast a given problem as a dynamic game, we need the following ingredients. We need first some joint dynamics, which describe the evolution of the state X. But now X involves the state not only of a single agent, but of n agents. And then these dynamics F, they don't only take a single input U, but they take an input for every player, so U1 to UN. And they take these dynamics take the same role. They are used to predict the state at the next time step from the previous time. And then additionally, because now we have n players making a decision in this system, each of the players has their own objective. And this objective can again be written as this cost function, but here now with index I. So player I has objective ji, and this depends on the states in the future, then on the states of player I itself, so ui, and then also, the inputs of player I, which are ui, and then also the inputs of everyone else, which is u not I. So we do note it like this. And now, because we have n different objectives, we cannot simply solve this as a single optimal control problem, because there's not one objective that we want to one cost function that we want to minimize. Instead, the solution will be an equilibrium, and a very popular solution concept is the one of a Nash equilibrium, which means that every player is sort of competitively doing this optimization for their own objective until they reach this equilibrium state in which no player can unilaterally improve their respective cost. So mathematically, that would be written as we want the costs of player I at the optimal input sequence to be smaller than all other costs that they could achieve with the when they change their inputs, if everyone else stayed at their optimal inputs. So you can sort of think of this as multiple players pulling at the joint state trajectory with their inputs in order to favor their own objective. Now, solving these kinds of problems is beyond the scope of this lecture. However, I do want to show a few applications of this kind of idea. And so the first example is this toy example from Forest Lane that he has used to encode a tag game. So two players playing tag, where the objective of player one is to minimize the distance to the blue player, and the objective of player two is to maximize the distance. So red is the chaser and blue is the evader. And the dynamics of each of these players is modeled as a 2D point mass. And you can see that by solving this game over these two players, we get this very competitive and highly interactive strategy where red is able to sort of chase blue into a corner and tag them. The second example that I would like to show is this work from Alexander Liniger from ETH Zurich, who has developed a game theoretic controller for racing of these model cars. And there the objective is for each player is to not collide with other players, but stay in the track bounds and stay ahead of other players, as well as maximizing track progress. And you can see that by solving this dynamic game over these two players, you get this very competitive wheel-to-wheel racing behavior on this model track for these toy cars. To conclude today's lecture, I'd like to summarize what we've discussed today. So we've started with a discussion of limitations of reactive control, which motivate the use of optimization-based techniques that we've looked at today. Then we've discussed how we can cast a given control problem as an optimization problem and how we can wrap this optimization in a receding horizon scheme to obtain a model predictive controller. Then we've discussed different design parameters in order to make a model predictive controller performant for a given system in practice. And finally, we've also reviewed some of the limitations of MPC in the presence of other agents and potential extensions to games. Now, if you're interested in this topic of model predictive control, there are several resources that I can recommend. If you're interested in model predictive control in general, there's this book by Francesco Borelli on predictive control, and there's also the lecture material from UC Berkeley available online. If you're interested in how you can solve the optimization problem that we had at the inner loop of model predictive control and how you can solve that without something like jump or Casadi, you can consult this book on numerical optimization by Notchodal and Wright. And finally, if you're interested in control in general and also like to consume this material in terms of videos, there's this very good YouTube channel by Stephen Brunton on this topic. Okay, with that we've reached the end of today's lecture. Thank you for your attention.